All right, so let's look at some applications of the third law. Is that all right? Or do you have more questions? Please feel free to ask questions. And there's the back channel chat that has been posted on Slack. So if you are shy, you don't want to ask questions in front of everyone, you can safely, ask questions on the chat. All right, so let's look at some consequences of third law. And I will be brief here. So one is that heat capacities go to 0 as T goes to 0. So heat capacities go to 0 as T goes to 0. So for example, we can take Cp, and Cp is given by T ds dTp. And this is given by ds by d log of T. So we see that, as T goes to 0, log of T goes to minus infinity. And since S goes to 0, delta S, delta log of T, this goes to 0. Okay, so this is the, this is one of the simple consequences of the third law. Another thing is that, objects don't behave classically anymore. And one of the things is that thermal expansion stops at small temperature. And this should be like intuitive from a microscopic point of view, because what is thermal expansion? Thermal expansion is kind of, if you take a solid, which is a lattice, and you heat it up, what's happening is that there's a lot of kinetic energy that the solid has, and therefore, the average distance between those guys, they are increasing. So when the temperature is very low, what happens is that all the molecules and the atoms, they settle down to the minima of the potential, right? So let's define the thermal expansivity or parameter. This is known as the isobaric expansivity. So what is it? This is basically the rate of change of volume of a system with temperature if you keep the pressure constant per unit volume. Okay. So now, since delta S, delta P, so delta, not P, yeah. So this goes to 0 as S goes to 0 and T goes to 0. What it means is that from Maxwell's relationship, this thing is nothing but delta V by delta T of P. And therefore, the thermal expansivity also goes to 0 as T goes to 0. Okay, so that's an application of Maxwell's relationship. Okay. So this is valid because S is going to 0. And there, okay, so there's an important, okay, before I go there, let me just recap the number 3, which we already covered.
Sir, sir, there is a formula like entropy is given by logarithm of number of possible orientations,
Okay.
arrangement. Yeah. So if I have a very ordered system, say my only arrangement is 1, then my entropy is 0.
Yeah.
In the temperature tends to 0, seems
Yeah.
to be the vibration gola quantum vibrations of these things getting smooth. These are getting very straightened out. Things are
Right.
almost getting an ordered phase. But we know that quantum mechanical fluctuations always are there, even at t goes to 0, right?
Right.
So, is there a perfect order out there as t goes to 0, or quantum fluctuations still there, but entropy is 0?
I think, well, so, I mean, I think here probably the word fluctuation is something, it's a bit misleading. Because, what we are doing at the end of the day is that we are counting states, right? So quantum fluctuations are so if I have a well-defined value of my Hamilton of the energy that is there, so it's some eigenvalue of some Hamiltonian, we have a number of quantum mechanical some eigenstates, right? So when we are counting, when we are calculating the entropy of that system, we are actually counting the number of eigenstates of that Hamiltonian.
Okay.
So of course, quantum fluctuations, when we say quantum fluctuation, what we are saying is, even if we have a eigenstate of the Hamiltonian, but if I measure, say, the position of the particle, which may have nothing to do with the energy, we are going to have quantum fluctuation, right? So that's not going to change entropy. And I don't know if you were there a little while ago. I talked about how the Hamiltonian ground state, even if there's a large degeneracy, usually the interactions will lift that degeneracy, and typically the number of ground states that we have is going to be very small. Does that make sense? That explanation of what is fluctuation?
Yes, sir. I think I
I mean, you're talking about like fluctuations, like, so yeah, you're talking about like how heat and creates fluctuations, and you're
so
saying
actually,
that is that
yeah.
fluctuation taken over at low temperature by quantum fluctuations? And my answer is
Yeah.
that no, because quantum fluctuations are really not fluctuations in the same sense.
Yes, quantum
Uh,
fluctuation.
in like, we know that in cosmology we do that, because in cosmology what we say is that, oh, there are quantum fluctuations of the initial state of the universe, and when we have inflation, those quantum fluctuations become classical fluctuations, right? So that's that's different. But here I'm saying is that when I'm counting the entropy from a quantum mechanical point of view, I'm calculating the number of eigenstates of the Hamiltonian.
Okay.
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 Well, good question. So that's my guess. Okay. Okay. So number 3 is that the ideal gas law already breaks down. We already saw that. Ideal gas law breaks down. Of course, it should have. It should, because no gas is ideal. Gases are not point-like molecule, like are not like billiard balls. And then the number 4, and often this is also, some people also call this the third law of thermodynamics, is that it takes an infinite number of steps, like isentropic steps. Isentropic means that where the entropy is constant, and what's the other one? Isothermal, right? To reach t equals to 0. Now, this is not something that I'm going to prove, but give a very heuristic sort of, argument. And so suppose that this is your TS diagram. So this is T, this is S. Now, if entropy did not go to 0 at, say, T equals to 0, so, so we have some ST curve for some value, say it could be pressure or something. So this is not realistic. Sorry, shouldn't go up so sharply. This is more like, it should be more like this. So this is some, say, x1 value, and so this is the x2 value of the same parameter. So the physical process through which we go down to t equals to 0 is that, well, we lower the entropy, we lower then that, but keep the temperature constant, and we lower the temperature. Sorry, we lower the entropy, keep T constant, and then we lower temperature, but keeping S constant. So this is, this is basically how we do this. So this is. So if the entropy did not go to 0 at T equals to 0, then there was a finite number of steps we could use to reach T equals to 0. But since entropy actually does go to 0 as T equals to 0, the real nature of this curve is different. So the curves actually look more like this. So, sorry, again, I'm going to be a bit more realistic. So these lines, these curves converge as T goes to 0. So, so if you go down to T equals to 0, the number of the size of the steps becomes smaller and smaller, and you get closer and closer to T equals to 0, but you can't really reach T equals to 0 in finite number of steps. Okay, so this means that the third law implies that absolute 0 cannot really be achieved realistically in a finite number of steps. Okay, but we can get pretty damn close. We can get much lower than the cosmic microwave background. Okay. All right. So, any questions? Yeah, I want to.
Does this have anything to do with the fact that adiabatic curves are asymptotic?
Yes. Yes. I think so. Yeah, I think so. Because asymptotically they are. Yeah. Because yeah, I believe so. Yeah. I can't prove it right now, but I believe so. Yeah. Any like both adiabats as well as isotherms, right?
I can't remember the equation for the isotherm off the top of my head, but I was thinking about the equation of the adiabatic curve.
Yeah, yeah. I think isotherms too, right?